We're talking in 6.3 about the concept of circular motion. And this will really later on affect rotational things. So we have to kind of have this down pat. And there's really a couple things that we want to talk about here. The first of these things is that the acceleration of an object in circular motion is v squared over r. Now, what is v? V is the tangential speed. It's the tangential speed. Okay? Now, technically speaking, v is a velocity, right? It's a velocity vector. The reason there's acceleration is because when something travels in a circle, at any given moment, the velocity changes direction. It doesn't change magnitude if it's assuming it's constant circular motion. So this might be spinning at like 3 RPMs. Well, 3 RPMs is the amount of revolutions per minute. We can then figure out the velocity at the edge of the circle, but the velocity is changing its direction. And if I were to show you this or demonstrate it, it would be like a person playing softball. If a softball pitcher releases at the bottom of her arc, the ball goes tangent to the circle. It literally gets launched like this. But if for some reason, this has happened before in baseball, it happens in softball, you like lose your grip when you're throwing. You ever seen a pro baseball player, this I've seen happen before, they'll go to throw it and it'll like fall behind them, and it'll like slip out, or they'll go to throw it and hold on too long and they'll like spike it accidentally, and it's just like your muscles aren't moving as fast as your brain at times. So that scenario here would be like, if a softball pitcher, instead of releasing at the bottom, released here, well, then it would be releasing here, and then the tangent looks like that. So the ball would move in that direction if it were released here. If it's released at the bottom, it moves in that direction. So the velocity is called tangential speed really here because it's always tangent in direction. So if you want to draw your velocity vector in at each location, that's your velocity vector each time. All you're doing is drawing a bunch of tangent rays coming off of the circle. And now that you've taken calc or you started calc, tangents should be very familiar in your language or in your understanding of where it is shown on a graph or where it is shown in motion. And it doesn't have to be a circle, as you know, to have a tangent. Any curve has tangents at any instant along the path. So the acceleration exists because the direction of the speed is changing. Remember, the value of v is not changing for these problems where it's uniform circular motion. It's the direction. It's the direction of v that is changing. Remember, a comes about from either a change in speed or a change in direction of the speed. That's why when the question is asked on like an AP exam traditionally, what things can accelerate or decelerate a car? What's the answer to that? What parts of the car could cause acceleration or deceleration? What are the things that you can use as a driver to accelerate or decelerate the car? Steering wheel, because that changes direction. And then the obvious ones, the brakes and the gas. Right? So there are 3 ways to accelerate a car, not just 2. Most people think the brake and the gas. The steering wheel just changes direction, which changes your velocity vector, and therefore it shows acceleration. Which way does acceleration act in these problems? Which way does it act?
I mean, I guess in the direction of motion, like tangent to the direction of motion. I don't know.
It's not in the direction of motion. That's the common misconception there, actually. Inwards. Inwards. So at all these moments, the acceleration vector is perpendicular to the velocity vector. Remember how a radius and a tangent intersect at a 90-degree angle? That's one of your geometry laws. Whenever a radius and a tangent occur at the same spot, they're perpendicular. All of these scenarios are right angles. You can draw them in if you want, but all of those are right angles. Your acceleration is called centripetal because it is center-seeking.
Isn't it how like sometimes it's the tension in a rope, or sometimes it's the friction?
It can be friction on the car and the tires at a bank turn. It's tension in a rope. It's gravity of an object orbiting a planet. It's the normal force from the wall on the gravitron. Ever got on the gravitron before? It's the thing where it spins really fast and the floor drops out, and then you get sucked up against the wall. Well, the wall is pushing you back toward the center. That's what's giving you that red vector toward the center. Now, if acceleration is directed toward the center, so must the force be? So therefore, our force is always acting toward the center also. So the blue vectors are F. Okay? The blue vectors are F. And that makes sense logically, just like Tristan said. If you didn't have a rope and you were spinning something, or let's say you're spinning something and the rope snaps, it's going to be launched off from the circle. It doesn't want to stay in this circular pattern because of inertia. Inertia tells us what? An object in motion will stay in that motion. Well, technically speaking, when this object is right here, which way does it want to go? It wants to go northeast. It wants to go in the direction of the tangent line. So if I were to literally cut the cord, when it gets here, it gets launched in that direction. The acceleration is what's keeping it moving in a circle. Without that acceleration, without that rope or whatever it is holding it in a circular motion, this object would not stay in circular motion. Okay, it would not stay in circular motion. That's the first formula. The second formula is simply F equals ma, which becomes F equals mv squared over r. So this is the first formula, and then plugging that in for A gives us the second formula. Those are the two formulas we're going to use in this chapter, or this section, or whatever. There's nothing new besides this. Now, the new stuff is going to be conceptually understanding what we're doing here. Okay, conceptually understanding. Your book talks about rounding a curve in a car, which is what Tristan mentioned, and then they talk about orbiting a planet, which is what I was mentioning. But again, as we said, many things take on what is called the centripetal force. Center seeking, centripetal, not centrifugal. Centrifugal is an effect. Anybody ever heard of a centrifuge before? Centrifuge? It takes blood and it spins it really fast so that it separates based on its density, or I think it's density it uses. And you get your platelets, you get your white blood cells, your red blood cells, all this different stuff you can test in different tests, whatever, different arrangements. But the idea is that the desire for the blood to go toward the outer part, or for you to get sucked against the wall in the gravitron, that's called a centrifugal effect. It's not a force. It's very misleading because a lot of students think centripetal and then centrifugal are the same thing. The effect of you sliding outward and going out, that's the centrifugal effect. That's all it is.
All that's actually happening is your direct, like your velocity is going this way, and the acceleration is pulling you inward. That's it.
And the inward acceleration is centripetal, because centripetal is center seeking. Centrifugal means center fleeing, going away from. So whenever you're talking about what's keeping an object in circular motion, it is the centripetal force, which is caused by the centripetal acceleration. Anytime you have acceleration, you must have a net force. You must have a net force. Okay, another classic example that the book talks about is, it's hard to draw, I'll try to draw it. I think I can actually. Here, let me draw on the next slide. So the other one that the text gives and likes to talk about is a tabletop. And that tabletop has some sort of a hole in the middle of it with a rope and a mass hanging at the end. And then that rope is connected to an object here. And what happens is, and this is actually straight out of the lab I did last year in my class, so Parisian Spence, you might remember this, with the pencil. Remember we spun that little thing, that lasso kind of thing, with the rubber stopper? I think you guys did something like that next year too.
Yeah.
Right? You spun something with like a pencil or something between, and there was a mass at the end. That's this problem right here, where this object is spinning in circular motion, causing it to be balanced by the weight of this object here. Okay, this is like a classic problem or a classic arrangement that you'll see for centripetal motion. And again, what are we noticing here is that there's some force keeping this object, let's call this mass 1, and that mass 2. There's a force keeping mass 1 in circular motion. And the direct force is tension. Indirectly, it's the weight of this object here, right? But the direct force is tension. It's a rope. A rope is connected through the table, and this object up top, you give it a spin and it starts spinning in a circle. Why doesn't it shoot off the table? Because there's tension in this rope that's keeping it in circular motion, and the tension in this rope comes from the weight acting on the rope at the bottom. So it's really the weight of mass 2 that's keeping this in circular motion, but that's an indirect effect. The mass is causing tension, the tension is keeping the upper object in circular motion. Which is why when we draw a free body diagram of this, mass 1 would look like this. Here's mass 1. Its motion is like this, and I'm going to just put it in one spot because I really can't draw in all these different positions. But right now, mass 1 has a force acting toward the center. That's what it has, a net force there. And that's a force of tension acting on it. And then if I were to draw mass 2, and technically mass 1, has weight going into the page. Do we see that for mass 1? Mass 1, its weight, I'm drawing a bird's eye view of mass 1. Think about this perspective. I'm drawing a diagram from above on mass 1. The tension acts toward the center. The weight of mass 1 would be acting into the table, which in this case is into the page. So I can't really draw that vector acting into the page right now. Does that make sense what I'm saying? Okay, I can draw it with an X technically if I want to. There's a way to draw vectors with an X for three-dimensional. So this would indicate that there's a force acting into the page. But you know what? There's also a force acting out of the page, the normal force. And weight and the normal force are balanced. So I don't really care about those two forces because they're not affecting the problem. But the second mass would have its weight pulling down, and it would have tension pulling up. Okay, so a problem like this, we would have two equations of motion. One would be a radial or circular equation of motion up here, and the other would be a vertical equation of motion only. No horizontal equation of motion here. Okay? Let me see real quick. Okay. So your textbook likes to take the adoption of everything acting out of the circle forces are considered to be positive, and every force acting into the circle is considered to be negative. That's the general adoption it takes. But you could do it either way. If you want to call into the circle positive and out of the circle negative, that's fine as well. It doesn't really matter which way you choose. Now, what does matter, though, is the sign of your A value, your acceleration itself. So let's look at this first example. This is on page 135. Okay, we're going to look at sample problem 6.04. It's a bicyclist. I'll draw it on the next page. It's a bicyclist going through a loop-de-loop. That's all it is. So the bicyclist is at the bottom first on the bike right here, riding the bike, and then the person goes up, goes around the loop, and comes back around and ends up over there. And the question is to investigate the forces acting on the bike as it travels through the loop itself. As it travels through the loop itself. So, the first position that the question wants you to investigate is at the top up here. I'm going to draw a box just to see here. When this bike is at the top of the path, right up there, this is the first question it wants to ask us. So, again, when an object moves in circular motion, which way does it want to move? Which way does it want to move? Yeah, it wants to move out of the circle, away, tangent to the path, but away from the center. So as a result, which way is the track pushing on the bicyclist at the top?
Into the cyclist.
Very good. Into the center, or cyclist. Very good. So the normal force from the track is pushing toward the center there. What else is acting toward the center?
Gravity.
Gravity in this case. So both of those vectors provide the centripetal force needed to keep this object from literally launching off at a tangent or away from the center when it's at the top there. So when we look at a problem like this, we have to consider the fact that we've got, and I'm going to draw toward the center positive because I got used to that. I'm reading your book and you could do it either way. The reason the book calls forces outward positive is because they like to measure the radius as a positive going outward. I don't think it matters, and I've never had a problem with it this way, so I'm going to adopt this method that I've used. So the way I would write this is this. I would say the sum of the forces centripetally or in circular motion equals MA, but A is really V squared over R, but A is really V squared over R. And Fc is really the sum of those forces, and we have two of them acting toward the center, Fn and Fg. So if you're looking at the example in the text later on, you're comparing it, you're going to see what the book does, and they label this as negative. They label this as negative, and then they label this as negative. Because they're saying, well, if the acceleration is toward the center, and they're considering away from the center as positive, then it would make your acceleration negative. So this would be negative here, negative here, negative here. So is there any difference really? Mine are all positive. I personally think that pulling toward the center positive makes life easier for you in the long run. Okay, that's just my opinion. You can choose the other way, it doesn't matter. But I'm just giving you my opinion.
So the only time centripetal acceleration is 0 is when it's not moving?
Meaning when something is in circular motion? First, for centripetal acceleration even to exist, it's got to be in circular motion.
Yes, yeah.
But if it stops in circular motion, it's not in any motion anymore.
Right.
Follow me?
So
Anytime anything is going through a curve with any velocity whatsoever, there absolutely has to be AC.
I'm saying like the only possible scenario where AC is 0 is when it's not moving at all.
But then it's not circular motion. Think about
Right.
it. It's not motion at
So
all.
then
So any problem that involves circular motion is moving. So inherently,
you're gonna have A.
precisely.
Okay.
There's always going to be an A in these problems, or else it's literally not moving, and then it's not even in circular motion at that point. Okay? It's a good question, though. I like what you're saying, what you're getting at there, because you notice that V is the only thing that can be 0 there, because M can't be 0. Anyway, so this is the equation of motion at the top. At the top. How does it differ at different spots? So let's choose other spots that make sense. Let's choose the east and westmost point of the circle, and let's choose the most south point of the circle here. So how would it differ? What do you think? Let's put them over here first. Now what is it going to be? Draw your free body diagram of that. What acts toward the center still? Give me more specifics. What force acts toward the center still? Normal force. It still pushes back against you because you're pushing against the surface.
For problems where it's like a plane, what force is acting toward the center? Or if it's like a plane.
Lift and drag force. Depending on what you're doing. You're talking about a plane that does like a loop in the air, right? Or barrel rolls and stuff. That's your lift and drag force. If it's going this way and it pushes you toward the center, that would be lift force in that case. If you were nosediving and doing a loop like that, it would be drag force then. Drag pushes a plane down, lift pushes it up. There is something called negative lift. We'll talk about that soon, I think. Yeah, pretty soon in this section. So yeah, the Fn pushes toward the center, but what's the obvious difference now?
Fg is opposite of velocity. Sorry, Fg is the direction of velocity.
Thank you. Very good. Fg acts down pretty much. It's acting tangent to the circle. Remember, Fg always acts down. So at the top, Fg and Fn together are providing the circular motion effect, or the forces. So this is the equation at the top there. And then we'll redraw the same thing on the left side here. So on the left side, I still start with the same basic governing equation, sum of the forces in centripetal or circular motion equal MAC. And then on the left side, though, what we have instead is simply Fn acting toward the center only. So that's what it looks like on the left side. Is the right side any different? Is the right side any different? I know the diagram looks slightly different, but my equation, why is that, Chip?
Because Fg is still pointing downwards and Fn is pointing towards the center and it's positive.
So because we're only looking at circular motion equation right now, and we're not really looking at our vertical forces and horizontal forces, we're trying to figure out what keeps it in circular motion. Left or right are the same. So let's jot down or right here. So the left position or the right position, either way, Fn acts toward the center of the circle.
Wait, why are we ignoring Fg?
Because Fg does not act toward the center, nor does it act away from the center. It acts tangent to the path. Remember, only forces that are listed under here are forces that act either away from the center or toward the center.
That's all that is relevant.
Correct. Now, there are other positions along the way that would be a little confusing, like right here. Because gravity, when pushing down, has a component tangent to the circle and a component toward the center. So these other positions along the way, FG will have a component of it, like a cosine theta or a sine theta part, that acts toward the center. Okay, I'm slowly building up to where we're going, okay? And then at the very bottom, when it's here, when it's in circular motion at the bottom, we know that gravity acts away from the center, meaning down, and the normal force still acts up. So my last arrangement, we've done top, we've done left or right. Now at the bottom, though, what would the equation read at the bottom? It would read, yeah.
Like the same as the top, right?
Close.
Or no, it would have Fn going upwards.
Okay.
And,
Fn is toward the center, which is positive,
and Fg downwards.
away from the center, which is negative. Try to be careful because it's very misleading to say up and down there because it is up and down. And it turns out, right, Tristan, that up is positive here because up is toward the center. And down is negative because down is away from the center. But that's only at the bottom. Follow me?
Yeah.
Because look at the top up here. Fn and Fg, we gave them both positive signs, didn't we? And they're both acting down. So it's like, wait, why are they positive? They're acting down. It's not about up or down anymore. It's around into the circle or out of the circle. Okay, that's what we're looking at here. So when we talk about things like bank turns and cars going around bank turns, which we'll look at in a moment, what is keeping it in that bank turn?
Friction.
Friction?
Air resistance.
Slightly. There's another component that's huge.
Inside out acceleration.
Another force. Banked turn. Think about a bank turn.
Centripetal force.
Car going around a bank turn would be on an inclined plane the whole time, wouldn't it? Not a bank turn, not a flat turn, but a bank turn. Normal force, a component of it actually. So we're going to have to break Fn into components now soon. So the problem gets a lot trickier when suddenly the turns are banked. And this is like a very classic AP problem. Car going around a bank turn. Because you're involving inclined planes and you're involving circular motion. This is a big part 2 problem, not a part 1. I mean, I could see it being a multiple choice and making it simpler. But this is a big part 2 problem because you're going to be doing stuff with kinematics, with circular motion, with inclined planes, meaning dynamics. So you're going to have a couple different things involved in a problem like that. Okay, so we'll get to the bank turn problem still. All right. Now, besides that, for this problem, the book then asks you to, I think, calculate something, right? It says, what does it say? Yeah, it gives you the radius of the loop, and it says, what is the least speed that the biker can have at the top of the path to still remain in contact? To still remain in contact. What is the least speed? So let's pause for a second and think about this whole process, okay? The least speed. So we want V to be as small as possible in that circumstance. But we're at the top of the path. So up here. We want V to be as small as possible. So if V is as small as possible, it makes the sum of these guys really small, doesn't it? But can Fg change? Assuming we're on the Earth only. Can Fg change? No. Obviously, big elevation changes it, but we're in a little loop here. It's not a big deal. So Fg is not changing if V gets really small. So what has to change if V gets really small for this equation to still be true? What has to change? The normal force. It's got it, right? So the idea is this, right? And first of all, how many of you got on a roller coaster before? Honestly. I'm not a fan, so I've never been on. Okay, you guys have. I have when I was a kid, but I can't go right away. I can't do motion, it's terrible. I wanted to be an astronaut. If you can't go on roller coasters, you can't be an astronaut. Anyway, so when you get to the top of the path on a roller coaster, if it's exactly the right speed, technically speaking, your weight pulling down is enough to keep you in circular motion. Remember that Fn and Fg both push you toward the center? This is a classic problem for multiple choice. The speed that you need at the top to just keep you in motion and not actually have the track pushing back on you is assuming that Fn drops off and goes to 0. And then V you calculate is the minimum V necessary. So let me explain that again to show you. So if we set this equal to 0 here, and we solve for v, we get fg times r over m, all underneath a square root. That's what v is going to give me at the top of the path. But because fg is really mg, this becomes mgr over m under the square root, which really just becomes gr under the square root. Let me just put a little line here to show you what we're working with, okay? All right. So we're working on the top, not the left, right, or bottom. So at the top, when it's reaching the top there, if your speed is really, really, really fast, you're going to want to move away from the circle. The desire of the object to move away from the circle is greater if your speed is greater. So that means that the track has to push back if the speed is a really large value. And again, that's logical here. If this number goes up by a lot, well, this number can't change, so this number has to go up by a lot. So if I plugged in a number for v as like 10,000, well, then Fn is definitely going to be there in this problem, assuming this number is not too large. But if I plug a number in like 2 for v, then there's going to probably be no normal force. So the faster you're going along the track, the more speed you have, as you go around turns, the more the track has to push back against you. It has to physically push back harder with more normal force if you're going faster. So whenever a problem says to you, find the minimum speed necessary on this arrangement to keep it in circular motion. The minimum speed is the instant when you no longer have the track pushing back against you. And you kind of feel like...
I was going to ask if you were going to feel weightless.
So you have that effect. So let's think about this for a second. Your gravitational pull is toward the center, right? Your desire or your inertial effect is outward. Those two things are going to balance each other there in that situation. So when you don't have Fn there, it's like you and the car are kind of like floating on the track there. You're not pushing against the track, so it pushes you back. You're not falling down with gravity because you have this mv squared over r that wants you to move away from the circle. So those are in a balance there. So yes, it's like the feeling of weightlessness, like when you have with a free fall, or like an elevator that's moving down with an acceleration of negative 9.8. Same concept, right? An elevator problem, we've done that one. When you're going down, you feel like you weigh less. So when you're at the top of the track there, the normal force may not exist if you're going at the minimum necessary speed. So the book gives you G, which is 9.8, R in this problem was 2.7, and you literally just plug those two numbers in. So this is really nice to write down somewhere, like a calculator program, so that when you're doing the multiple choice, I would write object in circular motion at the top of track. Minimum speed, and have that written down by calculator.
Just top, right? Just the top.
Only at the top. Absolutely right. Only at the top. Because when it's not at the top, now here, it can't be gravity. That's the only thing giving you the effect. Because gravity isn't even there.
And this applies to other things outside of just this type of problem, right? Like
Correct. Yeah, it absolutely does. So like a problem like spinning a rope. Spinning an object. I've got one here. I mean, I did it last year, so I guess it's a redundancy, but I'll just flip it around again. I bought a new one actually this year. Do you guys remember the one I used last year? I used this thing last year. Remember this? This one I built myself. Remember this last year in physics? I just attached a bunch of ropes, filled a cup of water, put this here. It was gross. Remember, it was all falling apart, and there was like a rope I attached to the end of it. And we just sat here and spun this like this a couple times with a full cup of water, no water leaked at all. Did you do this in honors physics last year at all? Did you do anything like this with a demo? So Mr. Donchek does a demo every year where he puts a hole punch in the cup.
Yeah.
He fills the cup with water and he spins the cup the whole time, and no water ever falls out. Because which way does the water want to go? It wants to go away from the circle. So as this cup is spinning, the water's desire is to move outward in tangent, but the cup pushes back with a normal force from the base. So it's the same concept here. I'm putting the cup on here, and the cup staying on here over and over again. It's nicer actually to put mass on there because it kind of just slips off the bottom. So the idea behind this is exactly that. And what Tristan just said is that when you get to the very top, you can slow down. And whether you realize it or not, when you're a kid and you're at the beach and you have a bucket of sand or a bucket of water, and your parents or somebody taught you that for the first time, that idea that the water stays in there, it's really weird, you naturally slow down your velocity at the top. You go like, you have to like literally spin faster at the bottom, you can slow down at the top, and the water will still stay in there. Because what's happening is, at the top, the gravity from the water wants to pull it toward the center. So there's enough center-seeking force acting that it doesn't need the surface of the bucket to push back with a normal force. It's the same thing as this. It's like the normal force not being there again, and the seat isn't pushing against you anymore. You're in that limbo stage where you kind of feel like you're floating there. So this would be the exact same solution for that problem with a cord spinning in the vertical plane. The horizontal plane is a whole other ballgame. When you're spinning a cord in the horizontal plane, that's the example you guys did and we all did with our labs last year. That's a different scenario. But I'm talking about spinning in the vertical plane. This is a horizontal plane. This is a vertical plane. Is that clear what I'm saying? Anybody ever see Doctor Who? Doctor Strange. No, Doctor Strange. Doesn't he create a portal? It's always like a vertical plane. Has anyone seen that movie? He does the same way you can jump through the portal, right? He always does like some sort of, that's the vertical plane. All right, anyhow, this generic solution can be very useful on a multiple choice question. You see what I'm getting at here, why I'm trying to help you with this stuff? It really benefits you to do well in multiple choice because you can still get a 4 or 5 in this exam and only get like one math problem right at the end out of 3 if you really do well in the multiple choice. That is the number one way to do well in the physics exam. Like there's 35 questions, if you can get like 25 out of 35 right, you could probably just get one of the 3 math problems right and not even do the other 2 and still get a 5 in the exam. It's very, very, very heavily curved. But that's only because the assumption is that a lot of students really do struggle with the free response at the end of the test. They're tough problems, they're not easy. And you guys saw today one example only of the one with drag resistance or air resistance or fluid resistance there. But again, I'm just trying to emphasize how important these small little tidbits of generic solutions could be for specific problems on multiple choice. And why am I saying multiple choice and not free response? Because free response, you gotta show your work. You can't just put this solution like, oh, because I remembered that it's a circular motion at the top, this is the answer. On a free response, you'd have to do what I did, which is show the equation of motion, drop off Fn, and then go through the process of solving. But on a multiple choice, it doesn't matter, you have to show any work. So on a multiple choice, if this is the problem, this is your solution. Without any work, pull up the program, you've got it written. So have specific cases illustrated in your calculator that we've gone over throughout the year so that you can utilize those to help you. Like the Atwood machine with the 2 masses, one on each side, this is a generic solution for that. If I recall correctly, it's larger mass times g minus smaller mass times g, all divided by the sum of the masses. That gives you the acceleration of the system every time. And that's the generic solution for the Atwood machine. So on the test, I guarantee you, you'll have an Atwood machine problem. So I recommend that you have the generic solution for the Atwood machine written in your calculator.
Where do you write the generic solution? I'm just curious.
I just make a program. That's what I. So I would go into the calculator and just start writing a program. Oh yeah, you have Atwood already in there. Nice. So yeah, it's exactly. Was that right? Yeah, I was right. Yes. I wasn't sure. I looked at it the other day. That's why. So
The same place as the quadratic formula.
exactly. But all you do is instead of entering a program, you just enter text. And then to see it,
You go to edit.
you go, instead of hitting program, if you try to run to Atwood right now, it's going to give you an error because it's just text. It's not going to run a program. So instead, you go to program, and you go over to edit it as if you're editing the Atwood program, and it opens it up so you can see it, and then everything in there is in there. Again, though, don't put everything in here that we've done this year because you're never going to be able to find it. You're going to run out of time. So only the really important stuff, like these generic solutions, that would be useful. Okay? So the Atwood solution is this, by the way. It's mg minus mg over m plus m, where capital M is greater than lowercase m. That's the Atwood machine problem right there. That'll give you the acceleration at any instant for an Atwood machine. There's also a generic solution for the force and tension in the cord. And if I recall correctly, it's, hold on. Oh, Lord. This is where my memory is terrible. Hold on. It's, the denominator, I think, is still, no, it's m times m in the denominator. No, it's m plus m. And this is 2, I can't remember. Hold on. I have it in my notes. Hold on.
Wait, what's this for, Mr. Allen?
This is the tension in the cable for the Atwood machine.
Oh,
And it's like 2, hold on, I gotta pull it up. I wish my memory was better. Remember I talked to you guys about memory? My memory is terrible. Since I've been a kid, I couldn't memorize definitions for anything. Social studies, I was terrible. Because I couldn't memorize dates and names and all this stuff. Oh, it was really bad. All right, general solution for Atwood. I'm doing it in the honors physics course right now. That's why I have the general solution written here. Here it is. I was really close. Okay, I thought I was. So it's G, M, M. That's the general solution for tension. 2G, capital M, lowercase m, over m plus n. Again, where capital M is the greater of the two masses. And for any Atwood machine, common sense tells you, if the bigger mass is on one side, it's going to move in that direction. Okay? That should be common sense by now, right? If the mass is the same, will it rotate? What are you in a state of? Yeah, equilibrium. But if the masses are different, it's definitely guaranteed to rotate in the direction of the larger mass. So this would be a clockwise rotation. Spence, go ahead.
Is that alpha or beta?
Oh, that's A. Sorry, A. I'm writing it quickly. So acceleration, but again, these are Atwood problems. This is not what we're talking about for circular motion. I guess it is in a circle, but all right. Let's get to a second example now for circular motion. Let's get to a second example. Which one do I want to do next? Okay, yeah, let's do this one. All right. So the next backup, sorry. The next example we're going to look at is 6.05. 6.05. It says the following. A modern race car is designed so that the air passing above it pushes down on it, allowing the car to travel much faster through a turn in a Grand Prix without friction failing. So normally, if you take a turn really fast and friction isn't enough, what will happen to the car? You slide out. You skid, right? You skid outward. But if there's a force pushing down on your car, that'll increase the normal force pushing back up. More normal force means more friction. Does that logic make sense behind what I'm saying? So as a result, what do race cars have on top of them? Spoilers. Well, wait, sure, but spoilers are actually the most important part. The example we're going to look at, I'll put equivalent of weight, really, right? And the spoiler works just like an airplane weight, except instead of lifting up, it pushes down. So the air running over a spoiler is actually running over the top at a much lower velocity than running under. This is Bernoulli's principle for fluids. Lower velocity on the top of the spoiler creates a higher pressure, which forces it downward. So with these problems with the race car, when we look at the race car going around a track or in motion, not only is the weight of the car acting down on it, sure, that's the weight of the car, but you also have what's called negative lift. Negative lift. And that's this FL, I'm going to call right here. Okay, so this is the car, and as the car is moving around the track like this, FL is the negative lift. So by adding in FL, it increases the value of Fn. Because if it's a race car, the general assumption, and hopefully it stays this way, is that the car doesn't leave the floor or the surface. If it does, then you could have a problem, right? So the general assumption is this. The sum of the forces in the y direction equals 0 for a car going around a racetrack. Now again, I want you to visualize this, right? I know it's tough. Look, that's the path we're talking about right now, okay? This car is traveling around that circular path, and I'm drawing it like an ellipse because I'm trying to draw a third dimension here. Okay, so the car is going around a path like this right now in the horizontal plane. A circle in the horizontal plane. Now, we know that something has to keep the car toward the center. What is that something for non-banked turns? Regular car, regular surface. Friction. So this is my free body diagram of a car in circular motion that has a spoiler on top of it. So the negative lift comes from the spoiler, the air pressure on top of it being greater than below it.
And so would that, the friction equal mv squared over r? In this case, because...
Absolutely. There's no other forces acting radially or toward the center or away from the center. So absolutely right. So the y direction, I'm going to do the y first at the top. The y direction looks like this. Fn minus Fg minus Fl equals 0. But as Chip just said, the sum of the forces acting radially always equal mv squared over r. Well, the only force acting radially that's acting inward is friction. But here's the thing. Friction is mu Fn. So this is what the equation becomes now. So what am I noticing? Let's take a look and let's think about this, right? I want you guys to understand the math behind it. Take a look at this last equation at the bottom here, right? Let's say we've got a value for v right now. And suddenly, I increase the value of v. Okay? I increase the value of v. Mu cannot increase. Mu is a ratio between the tire rubber and the concrete ground, or whatever ground is made out of concrete, I think. Mu is not going to change. So if v goes up, what needs to change for us is Fn. Let's talk about this now. Keep going. Does it 5 connect? Keep going. Fn goes up, why now? If v goes up, and velocity goes up, it actually increases FL. The lift force on a plane is a function of velocity. That's why when a plane takes off, it only takes off at the end of the runway. It doesn't just take off out of nowhere, right? It has to acquire a liftoff speed for the lift force to be great enough to literally lift the plane off. Lift force is a function of velocity, just like drag force is. Remember, drag force is either kV or kV squared. Lift force, whether it's v squared or v, I'm just generalizing right now, is a function of velocity. So if the car starts going faster, v goes up, so therefore Fn has to go up. But if v goes up, so does Fl. And if Fl goes up, so does Fn. How do I know that? Because look, solve this one up here for Fn. Fn equals Fg plus Fl. That's Fn. So if I start getting a larger v value, that means that the lift force goes up. If the lift force goes up, that means the normal force goes up, which would causes this to go up right here. So the only way to balance higher speeds and not sliding off a track, besides banking the turns, which we're going to see later, the only way to balance that option or that happening is to increase the normal force. But to increase the normal force, I can't just increase the mass or the weight, because the weight is a constant. The weight of this car with the person in it is not changing. Well, technically, fuel is being burned. So your gas tank is decreasing in weight. That's actually a big thing with rockets. I don't know if you realize that. When rockets burn solid rocket fuel, the mass of the rocket decreases dramatically. And it decreases at a rate. Related rates, calculus, related rates. Rockets are, a lot of them are solid. Oh, am I right? Is it both then? But originally, solids were used only. What is it now?
The small one is solid, and then the really, really big one is liquid.
We talked about this in engineering, remember? That's what I had. So I think the premise behind solid rocket fuel was that so the mass didn't fluctuate and move physically, and also because of its volatility, right? It's safer to have solid rocket fuel than it has to have liquid rocket fuel. So they used solid rocket fuel for like a really long time. I think now it's both.
It's both. It's more efficient because liquid rocket fuel is better in space.
It's better in space. So what I'm getting at though, obviously here, is for the car traveling around the track, when it burns fuel, technically it's getting lighter in weight because all that combustion coming out of the back of the car is mass. And mass cannot be created nor destroyed, just transferred. So it loses mass in the car, in the gas tank. So technically what's happening is Fg is going down, right? This number is getting lower because mass is being burnt. The fuel is being burned. So we're actually losing Fg, which means we're losing Fn. So we really need to combat that. So Fl is the one thing that will cause Fn to go up because you have more velocity. Okay, so this whole problem and the whole premise behind it is recognition of the fact that we have multiple forces acting on an object when it's in circular motion. So let's replace Fn with its equivalent expression here. Let's plug that in for Fn in the formula, and this formula becomes mu Fg plus Fl equals mv squared over r. And the problem in the text is asking you to find out what the lift force is. In the textbook, they say solve for Fl. So let's divide by mu. Oops.
So would that be lift force or like a drag force?
It's negative lift, it's called. Negative lift. I know, which sounds crazy, but it actually
It's
is.
not like the same thing with drag, where it's like the weight is being applied.
Correct.
It's intended to.
Correct. It's intended to.
So lift kind of means intended direction rather than just off.
Yeah. Exactly. It's not about up or down. It's about the angle of the spoiler. If the spoiler were angled the other way, it would create lift force. So you know how like airfoils have a certain pitch to them? The airfoils are wings of a plane. Have a certain pitch. The pitch for the spoiler would be the opposite. Because you want to push down on a spoiler, whereas on a plane you want to push up.
When planes land and they drop flaps to landing flaps,
That's increasing drag force, is what they're doing.
because aren't they redirecting?
The flaps suddenly go like this.
Yeah, aren't they increasing
And all that
the
air.
drag technically?
No, because
Wouldn't some of the air be redirected downwards?
but the lift comes from high velocity on the bottom. No, really high velocity on the top of the wing. So by changing the angle on the top, you're having more cross-sectional area, which increases the drag force. Does the lift change? It probably changes, but the drag force becomes much more valuable when it does this versus when it's flat. So the drag force technically overpowers the lift force, which is what causes it to start to fall.
When planes land, they fall really weird. Like,
I don't know. I haven't studied aeronautics as much. I probably should, but yeah. What do you mean by fall weird?
Like it's like a controlled rate, in a sense.
That's usually just the computer system that's doing it, though. Yeah. There's feedback loops in that system that say, like, you know, every couple seconds you want to drop a certain amount. So those angles on the wing, that's not the pilot. You know that, right? The pilot does nothing of that. The pilot literally either increases or decreases the amount of knots.
Well, not necessarily. It depends on the model.
I'm talking about like the big aircraft carriers, like commercial airliners.
On the big ones, it's actually the pilot more often.
Is it really?
The smaller ones, it's usually a commander.
Really?
The bigger ones are.
I would think it'd be the opposite, because I would think the big ones you'd want to rely on the electrical signal, not the pilot.
It's easier to fly the bigger ones because there's so much mass that you're moving from control-wise. Like it feels like it has such a fine controller.
So like a small change with a bigger mass isn't as effective as a smaller
It
plane.
feels really like more stuff.
Interesting. That's wrong. So point being here, though, right? We have mu and r in the denominator now, and that's fg plus fl still. And then if we solve this, we can move fg over. We'll get fl equals mv squared over mu r minus fg, which is really just mg. All right, subtract this over as mg instead. Just so everything's in terms of mass. So this is the lift force on a car going around a circular track with a given coefficient of friction. Another thing that might be worthwhile writing down in a calculator program if you're looking at lift force as a generic solution for a car going on a track. Not a bank turn. We'll get into bank turn in our next example, but this is not a bank turn at all. It's going to change dramatically with a bank turn. That is kind of where I wanted to end. So this works out really nicely. So we have the bank turn left for this problem. That's really the only one that makes it a little bit more difficult. I haven't introduced the problem with tension here. Notice that? But it's the same thing. Instead of FF being here, replace FF with FT, and now it's a tension problem. That's the only difference. And with a tension problem, maybe you don't have lift pushing down anymore, right? Because it's a tension problem, you're probably swinging in the air. So that's how it would change that value. But for this concept, I want you guys to start thinking about the idea that all these forces are interchangeable. So really quick, just so you know, is it Monday the trip?
Yes.
Okay. Who's going on the trip on Monday that's here right now?
Us three and
Three?
then Matt.
And then Matt. So Matt's missing 2 classes. So he's the only one missing 2 classes. So next class, I'm going to continue 6-5. I'm going to go into the bank turn. And then I'll probably...
Just 6'5"?
Sorry, 6'3". 6'3", sorry. Honors, different numbers. And then I'll probably do an example or 2 of tension just so you can see what it looks like. Okay, so we'll get to circular motion. If you want to start homework for 6-3, I'll definitely try to assign it and put it on Moodle either later today or maybe tomorrow later in the day. Okay, so if you want to get a head start on 6-3. After this, we're done with forces, which is nice. We'll get into energy and momentum as like the next 2 major chapters, and then we have to get into rotation still. Okay? So this 6-3 is really the last topic for the second quarter. The next test is going to be like 6-1 again with friction. You're going to see it again for sure because it involved in 6-3. 6-2, which is drag force, and then 6-3, which is circular motion. That'll be your 3 topics for the next test coming up. Is that clear? And then the third quarter, we'll do energy and momentum. And then the fourth quarter, we'll really focus on rotational stuff and harmonics, which is vibrations. That's kind of where we're going.
This is so
But
good.
here's the good part, really, here's the good part. If you can master mechanics and dynamics and circular motion and energy and momentum, the topics that are the easier ones, sorry, it's a lot. But if you could do really well on those, the rotational stuff is really only like one problem of the part twos. And it's a couple multiple choice. And the harmonics might be one problem in part two. So what I'm saying is, we really want to focus on mastering the beginning stuff, and then at the end of the year, we'll focus on that. And that other stuff later is all integration, which we haven't done in Calc yet, or you guys haven't done in Calc yet. So it works out nicely that it's in the fourth quarter, actually, because we're going to do all integration for that stuff. So it'll be a little bit tougher in that sense, because it's more calculus.
We're starting integration now, so.
Yeah, you were saying you're doing area under the curve and stuff. There's just a lot of formulas that you'll be using, and then the logarithm and the exponential function are applied a lot. Hey, take more banana bread if you want. If anyone wants more to take for the road, feel free.
So good.
Like it in the end? Yeah. Driven yet, you're probably wondering, like, why does this even matter? But we're going to do a problem that shows why it matters. And if you have driven, you'll notice that this happens a lot when you enter or exit highways. So when you take an entrance ramp or an exit ramp, and you'll see signs on exit ramps and entrance ramps that say things like max speed 40 miles per hour, and it'll show a picture of a truck tipping over in the actual image. It's a street sign that's very standard one on exit ramps. Because if you take an exit ramp at too high a velocity, what's going to happen is the truck itself or a SUV would easily tip. So they put a picture of what looks like a truck to emphasize that if you're driving something like a Jeep or an SUV of some sort, a Yukon or something, it could very easily tip if it's top heavy or if it has a lot of height to it, especially 18-wheelers and things like that. So the banking of the turn physically supports the motion. Because naturally, as we've talked about, when something spins in circular motion, it wants to move away from the track. So either one of two things. Either it's preventing this car from literally sliding off the track into, like, say, a bank or some sort of an embankment on the side of the road, or it's physically providing enough force in this case to keep it in circular motion and not tilt. So this car could do one of two things to fail. It could physically tilt that way as you turn really fast. And I'm going to show you this with the eraser. So the eraser's going around a turn. It takes a turn too fast, the car could literally flip like that. Because the desire to move outward from the top of it has a bit of moment of inertia we're talking about a little bit later, but it causes it to rotate on the side. But again, you could also, instead of taking this turn properly, you could slide outward instead of continuing to take the turn. So the normal force is going to be part of what's going to help it. And the rationale behind this is because the normal force is acting perpendicular to the plane. So if the normal force acts like this, part of it is pushing toward the center, part of it is pushing up. And the part pushing toward the center, that's going to be our mv squared over r in this problem. If we introduce friction then, we have to look at the case where now there's friction between the tires. But the first scenario, it's going to be frictionless. So the problem is the following. It says, curved portions of highways are always banked, tilted, to prevent cars from sliding off the highway. When a highway is dry, the frictional force between the tires and the road surface may be enough to prevent sliding. But when the highway is wet, the frictional force may at times become negligible, meaning that the surface, especially when it begins to rain, all the oil comes to the surface. That's the most dangerous part about driving, when it just starts raining, because the water displaces the oil in the pockets of concrete, or in this case asphalt under the ground, and the oil that's stuffed in those pockets, because it's less dense than water, comes to the surface, which is what hydroplaning is really. When you hydroplane, your car is riding on a thin layer of either oil or water on the top of the road, and it starts to lose control. So in this case, what they're saying is when it's raining, sometimes the frictional force is practically just negligible. It's really not helping you at all because there's that much rain that's making the road slick when you're going around a bank turn. If you're driving straight, then the frictional force is not going to be something you really need as much, but it's around the turn. So as a result, if friction is negligible, the banking of the turn is essential. So for this problem, we're going to assume it's raining and there's no friction involved at all. And then we'll take a look at a problem that does involve friction afterward. Okay, so let me just zoom out real quick so we can see this a bit better. So it says here that this figure represents a car of mass m that moves at a constant speed of 20 meters per second. So let's start with that. moving at a constant speed of 20 meters per second around a banked circular track with a radius of 190 meters. It says it's a normal car rather than a race car, so we're not going to have any sort of negative lift to take into account with a spoiler like we did in the last problem. Frictional force can be negligible. As a result, what bank angle prevents sliding in this problem? So what bank angle? And the answer we're going to get is going to be the lowest angle possible. Because the more it's banked, the more it prevents sliding. And think about that logically, right? If it were banked so much that it were 90 degrees, then your car would be running around the inside of this track, which I think I showed you guys last year in physics. It was called, oh my gosh, it was like the cylinder of death or something. It was one of the videos. Yeah, where they were driving around on motorcycles on the wall. And if you check this out, it was on my Moodle page last year. Maybe I'll send a link to it, but I forget what the phrase was. But if you drive fast enough with something like a motorcycle in a really, really small chamber, you can ride along the inner walls if you're fast enough for the velocity, because it's pushing back against you, the normal force. But anyway, that's a video. Yeah.
Yeah, there's something like that, but it's a ball. Like,
Yeah, and it's exactly, and it's the same concept of like the gravitron I talked about last week. It's stuck to the wall because you have enough friction between you and the wall. Now, the motorcycle also involves friction and normal force. For this, though, we're assuming no friction for now. But we want to figure out the angle necessary to keep it from slipping. So anything greater than this angle is the answer. So at the end, when we get an answer, say it's 12 degrees, theta is greater than or equal to 12 degrees is our answer, really. Unless it says, find the minimum angle necessary. Here it just says, what banked angle theta prevents sliding? So we'll find that angle, and then we'll make a statement at the end that says, any angle greater than this will prevent sliding. Anything less than this, it will slide off the road. So let's take a look at how we're going to do this. So the way we're going to approach this is a little bit different. Initially, you're going to want to use inclined planes the way we did in the past, where we tilt our axis. And that can work, and it will work if you do it that way. But it actually turns out for these problems that it's a bit easier not to angle your axes, not to tilt your axes. So let's discuss what the free body diagram should look like here. So the way we're going to draw it is we're going to draw our object first. Here's our car. Now, if this car is acting and it's going along this banked turn, the normal force will be at some angle, just like it's been in the past, coming off the plane. Okay, the plane, I'll draw the plane with the dotted red line so we can see it here visually. Okay, we're taking a cut of this car going around the turn. So imagine I take a slice from where the car is. That's what it would look like right there going around the banked turn. Now, my weight always acts down, so that's this way. Now, that's the only two forces acting. The only two forces acting on this object. There's no friction in this problem. If there were, friction would act down the ramp because the car would want to slide up the ramp. It would want to slide off the road to the right. And again, I'm taking a snapshot of the car on the right side of the track right now. If we're on the left side, we'd have to reverse everything about my plane. So I'm specifically looking at this. I'm specifically looking at this scenario that's listed on the right side, right here. That's where I'm looking, on the right side. Okay, but again, it would work on the left side. Everything would just switch though as a result. So what do we have to do for this problem? First, we have to recognize that Fn is acting at an angle. So if I think about this, let me label angles here. This is the angle theta right there. Okay, that's the angle theta. So if I were to draw a horizontal and a vertical from where Fn is acting, which angle is theta for Fn? Is it this angle or is it this angle? Chris? It's the top angle. And part of it is also just looking at the diagram, you can almost see it, right? But if you do a little bit of trig work here, you'll recognize it. And here's how you can quickly see it. Let me take a look up so you can see what I'm doing, right? So let's say angle's 20, theta. What does it make this? What does it make this? If this is 20, what does it make this angle right here? 70. If this is 70, what's this angle here? If this is 20, what's this angle here? If this is 70, what's this angle here? You see how I'm working my way around? Look, it's 180 degrees, isn't it? So because I know this is 20, follow me again, that's 70. These add up to 90, which makes that 20. These add up to 90, which makes that 70. These add up to 90, which makes that back to 20. You see how I'm working my way around? Okay, so the angle theta in this diagram is actually also right here. So when we do this problem and we break Fn into its components, we're going to draw one of its components along the horizontal dotted yellow line. We're going to draw the other Fn component along the vertical dotted yellow line. We're going to have to recognize that we're giving the angle with respect to the y-axis here. And we've always talked about cosine and sine working for x and y if you're giving the angle with respect to the x-axis. So because we're giving the angle with respect to the other axis, what should we do with our trig functions? What did we do with our trig functions when we did FG? Just switch them. Make the x sine now and make the y cosine. You could also label this angle as 90 minus theta and use that angle instead. And we could say that, Fn in the x direction is really just Fn times the cosine of 90 minus theta. But I'd prefer to say, you know what? Fn times the sine of theta is the same thing. This is for the Fn in the x direction. I would recommend using this option. And the same goes for Fn in the y direction. Fn in the y direction is Fn sine of 90 minus theta. But instead, I'd rather write Fn in the y direction as Fn cos theta. So in a moment, I'm going to redraw the free body diagram to break up Fn. But what are we doing physically? We're looking at the y component and the x component. So if you're going to use this angle, 90 minus theta, you keep cosine and sine the correct way. But if you're going to use the complement of that angle, you could switch your sine and cosine and just use theta. Either way is acceptable in this problem. You could start with this way, right, in the y direction, and this way in the x direction, and you could use this right here, and you could use this right here. Both of these work for x and y direction, but I happen to like doing it this way instead. Okay, and again, it's only because I'm giving the angle with respect to the vertical. And I'm giving the angle with respect to the vertical, just switch sine and cosine. Whereas if I'm giving the angle with respect to the horizontal, keep sine and cosine where they should be. This is exactly the same thing we did when we broke up FG into its components. Now, why did I not tilt my axis? Anybody have any idea? It's a little bit weird, this question, right? Because normally I'd say like, oh, I'm going to tilt my axis, so I'll say out of the plane is the y direction, into the plane is the negative y, down the ramp is the positive x, up the ramp is the negative x. But I didn't tilt my axis here, and I'm not going to. What do you think?
The force is going to act across the horizontal axis.
What force?
I don't know.
Centripetal.
No, centrifugal.
Yeah, the centripetal force that we're looking for here. The thing that's keeping it in circular motion. The thing that's resisting the centrifugal effect. Remember, it's opposing the centrifugal effect. The thing that's keeping it in circular motion is the normal force and the x component of it. So really, this is what we've got. This is Fnx in blue right here. That's what Fnx is. And in green, this is Fny. And in our problem, once we draw that, what can we do? We can erase or get rid of the vector Fn. Now that doesn't matter, so I'm crossing it off. So now if I look at my free body diagram, this allows me to state what Chris just made as a statement, which is Fnx is what is providing the centripetal force in this problem. Think back and remember and recall, something provides centripetal force every time. It's not just a mystery, right? It's either tension, friction, gravity, normal force component in this case, but something has to keep the object in circular motion, and in this case, it's Fnx for sure. So when we look at our free body diagram, at this point in time, we can do a couple things. First, we can look at the y direction and say we've got Fny minus Fg equals ma in the y direction, which is definitely going to be 0 in the y direction because the car is not lifting off the ground. So that would be my equation in the y direction. Now, the thing is, the equation in the x direction is very tempting to write Fnet equals max because we call this the x direction. but really the blue vector acts toward the what? Center. So what kind of a force is it? Really, it's a radial force. It's the centripetal force. So what are we going to do is we're going to say that this is the equation in the y direction, and then the radial direction, if you remember, was sum of the forces centripetally equals mv squared over r. And that's not going to be 0 here. Remember, this is not 0 because we have a velocity. The speed is 20, so the velocity is changing as the car angles differently each time, and we have a radius. So we're really going to use this second equation here. And the second equation is going to yield, let me just erase the bottom so we can keep running with this. The second equation is going to say the following. It's going to say Fnx acts toward the center, so we'll call that positive, and that is the only force acting toward the center, and we'll call that mv squared over r. So, if it helps, if it mentally helps you, keep in mind that this car wants to slide off the track, so there must be a force acting inward to keep it. What is that force? In this case, it's a component of the normal force pushing toward the center of the circle the car is going in. Yes?
Can you explain how that doesn't equal 0? Because wouldn't the force going out of the circle equal the force going in if it were to stay on the track?
Remember, when an object turns around a track, it's changing direction. Change in direction indicates change in velocity. Change in velocity assumes acceleration. So that's the way you want to remember. I get what you're saying, Max, totally. You're thinking of it as equilibrium, and that's a good way to think of it. It is. But it's not actually in a state of equilibrium. The normal force pushing in balances the centrifugal effect to want to move out, for sure. This is the centrifugal effect of wanting to move out, actually. We don't write it as a force because it's not a force. But the desire for the car to want to slide off the track comes from mv squared over r. So we actually are doing what you're saying. And we're saying that the force inward balances the effect outward. So the effect outward, though, is a type of acceleration because velocity is changing, because the direction is changing.
And so how do those two relate to each other?
Which two?
The sum of the forces in that.
This means the sum of the forces acting toward the center equals m times a acting toward the center. But a acting toward the center is v squared over r. Remember, centripetal acceleration is always v squared over r, so this is really ma, but I'm replacing with v squared over r. And then I carry down and say, what are all the forces acting toward the center? Well, it's only the normal force, x component in blue, that's acting toward the center of the circle, so that must equal the centrifugal effect wanting to pull outward. Okay, good question. Because it is a type of equilibrium when you think about it this way. Now it comes to just substitution. The normal force toward the center is Fnx. We can replace it here with Fn sine theta, and that'll equal mv squared over r. The question is asking us to figure out the angle theta necessary. So my recommendation is probably figure out Fn in the y direction. Over here, solve for Fn. We'll replace it in a moment so we can plug it in over here. Because if I look at the radial direction at this point, I'm stuck, right? Look at it, logically, I'm stuck. Mass is not given. Anybody notice that? Yet it's in my formula? So what do you think is going to happen to mass?
It's going to have to cancel.
It's going to cancel. V and R are given, aren't they? So we're good. So take a look where I'm pointing, because this is really important. These are given, not given, so it'll probably cancel. Not given, because we're solving for theta. And Fn we could probably get from over here. So let's continue to expand our equation in the y direction over here. So this equation continues down. Fny is Fn cos theta minus mg equals 0. So solving for Fn, we're going to get mg divided by cosine theta. We solve this for Fn, we move the mg over and divide by cos theta. So that's the expression for Fn. We'll take this expression for Fn and plug it in over here. Notice what happens? We get a lot of stuff with tangent and cotangent in these problems. Pick up on that by now? You guys noticed that with your lab, right? It was the tangent of theta that mattered there. So in this case, we're going to see the same thing happen. This becomes mg over cosine theta times sine theta equals mv squared over r. This is now my governing equation when we combine the y direction and the radial direction. I'm going to use the word radial a lot. I used it last year a lot. This book doesn't use it, but I like the word radial because it's not always clear when I say FC. So you can say the sum of the forces in the radial direction. Call that an R instead of a C if you want. It might just make it easier for you to understand it's along the radius that we're talking there. Both sides of the equation have m, so as you guys predicted, m drops off. Not the m we have here in the class, but the m here in the problem. So m cancels on both sides. We have a sine over a cosine here, which gives us a tangent problem. So we'll continue this up here. This becomes g tangent theta equals v squared over r. Move the g down to the bottom. Tan theta equals v squared over, that's a v squared over gr. And then theta equals the tangent inverse of that statement. And we are given all of this information. And notice, when friction isn't applied, the mass doesn't matter. But the mass will matter when friction plays a role. Okay? And I know in the lab the whole idea was like, oh, friction shouldn't matter based on the mass. It really shouldn't, but it really does actually. And we'll see that in this bank turn problem. Okay, we get the tangent inverse of v squared over gr. V is the velocity, r is the turning radius, g is the gravitational constant. So if you change planets, you change the angle. If the radius were to change, you change the angle. If you change your speed, you change the angle. So these are the three parameters that the angle theta is based on, and the only three parameters for this problem. So what's the hard part for this problem, really, in your mind? What's the hard part? Honestly, I'm honestly asking your opinion. Because I think there's a certain spot that's the hardest part, but I want to know in your mind. What's the hardest part of this problem? Look through it again. What's the part that you were like, how the hell did I come up with that? Or, I don't really get that piece. Like, what part was it that was the toughest?
Free body diagram.
I would agree with that, I think at least. The free body diagram is the toughest. I could also see, maybe forgetting to use mv squared over r here and using some of the force in the x as opposed to doing this. But I think the free body diagram is the hardest part for this problem, actually. And I think that's going to be the case for a good amount of the problems with forces on the AP exam. Your free body diagram is really worth a lot of points, whether it's physically worth points in the test or worth points later on, because your equations always come from your free body diagram. So for the banked turn problem, you want to recognize that the radial force is not going to act down the plane. It's not going to act perpendicular to the plane. It's not going to be either of these two forces. It's always going to act towards the center of the circle. So it's going to act at an angle off the plane. That's the blue vector we're seeing in the free body diagram. The blue vector is what's keeping it in circular motion. So that's what goes in for the sum of the forces radially as F and X. Okay? I don't know what the number turns out to be. It doesn't really matter as much, but we could plug in. Did anyone try it and get a number?
12.
Is that what it is? 12 degrees?
Yeah.
Yeah. 20 squared over 9.8 times 190, tangent inverse of all that. Yep. So we're going to get theta is around 12 degrees. So a 12-degree bank turn is necessary if the turning radius is 190 meters, and if, these are big ifs, right? And if the velocity of the cars are only going to be up to 20 meters per second. So, what do you think they do when they design roads? They put in what's called a factor of safety. Factor of safety. It's an engineering term that I've never discussed yet, but a factor of safety is used. Same with elevators. You get on the elevator, it says what? This elevator can hold 2,000 pounds. That thing can hold like 10,000. But it's a factor of safety of 5. Why? Why is the factor of safety so extreme in that case? Think about what would happen. It failed. You would die, right? You think the factor of safety on this chair is 5? No. It might claim that this chair might claim it could support, 180 pounds. It could probably support like 400 pounds. It's probably a factor of safety of 2. Because if the chair breaks, you're going to die. No. You're going to fall, but if the chair breaks, it probably indicates you need to lose a little bit of weight. It's probably what tells you, actually, right? More than anything else. Which is actually kind of sad, because I've seen it happen with overweight people. That's really sad to see. Don't ever laugh at something like that. It's really embarrassing. I've actually seen that before. Sorry, I'm getting mad about that. But the factor of safety on an elevator is 5, because if it fails, people die. So here is very similar to the concept here. So for example, if the speed limit on the road is 55 miles an hour, All right, say it's New York, not New Jersey, where it could be like 65 or even higher in the western country. 55, they're going to model this for something more than 55 miles per hour, just in case. Just in case. And there's a good chance that, like I said, when you exit the highway, it'll say like, what does it usually say? Ramp speed, 35 miles an hour, indicating to you when you get off the highway, slow down. Don't take it at 55 miles an hour around a turn because there's a good chance your car's going to slide off the road. So they'll give you a lower speed, but then they'll actually bank the turn enough for a speed probably double or triple that lower speed. So say the lower speed says 35, they'll probably model the angle to be up to like something like 70 or 80 miles an hour. Even though you should never do it, and it would be your own fault, they're probably still going to do it to give it a little bit of factor of safety there. Next.
The common safety factors for elevators is 11.
Is that what it is?
Yeah.
See? See? 11. So even 2,000 pounds, we're talking 22,000 pounds. Yeah. So there's a lot of structures. In engineering, you learn about classes of structures. If it's class 4, factors of safety are through the roof. Really, really large numbers. Class 1 is like, you know, like those antenna towers you see for like cell phone signals? If those fell, there was nothing in the air, does it matter? No, really. I mean, money-wise it matters, but it's going to harm human life? It's class 1. So class 1 is like, it would never harm human life if it failed. Class 2 is human life to be injured, but you're not going to really die as a result of like a chair breaking. Class 3, believe it or not, in textbooks, is like, they say this is not class 2 or not class 4. That's all they classify it as. And in class 4, yeah, which is ridiculous because that's like stating the opposite of what it is. But class 4 is like, if it failed, people are going to physically die as a result. Like a building, if a building just collapses on itself, people that are in a building are just not going to survive. You might, I mean, there might be a miracle. We've seen those before, right? Ever seen those like stories about somebody who like a building was collapsing and they like jumped out the window and literally were like on top of a piece of concrete the whole way down, and somehow when they landed that like broke their fall. There are stories of people like surviving ridiculous things, but generally speaking, if a building fails, people inside are going to die. It's going to happen. All right, so that's a bank turn without friction, right? We all agree without friction. Now, we want to also look at a problem that is with friction. Let's start by asking this. If friction were involved, what would happen to theta? If friction were involved in this problem, what would happen to theta? Mondell. Very good. Why? Give me some logic.
Because the friction is acting towards the center.
Very good. The friction is helping the centrifugal force. It's acting in addition to Fn sine theta, right? So it's pretty much assisting it. So we don't need as much of a banking there to keep you safe. So let's re-look at this problem with a frictional coefficient necessary. So I'm going to give you the friction coefficient. Then later, I think I give you guys a homework problem out of this section that has you determine mu, the friction coefficient. It's number 56 in the text. That'll have you determine it. But for this, I want to do the same problem, but now I want to incorporate, I'll give you mu, and we'll recalculate theta. Okay, so same problem, and now we're just going to write down, so let's do like part 2. I'm just going to move this down. Same exact problem, but now mu equals 0.15. And I just made that number up. It really doesn't matter what I use, okay? I shouldn't say that. It does matter, actually. Obviously, the larger the number, the more friction. So a number that's greater than 1 is usually not often seen with friction coefficients. It's usually between 0 and 1, but it can be greater than 1. So 0.15 is a low friction coefficient. Just so you know, numbers-wise, Teflon, which is very low in friction coefficient, from your lab was around 0.2, right? 0.18, 0.2, something around there. If you think back to the lab with the inclined plane, that was the value you got for that. And that's the same value you'll get for any Teflon surface, but it depends on what it's on. Remember, it's always the constant of 2 surfaces interacting that gives you mu. So this is a very, very slick surface right here. So this might be where it's been raining for a while already on the road, okay? So mu is 0.15. Now, what do I want to do? I want to redraw my free body diagram. But it's not going to be very different, right? So I'm going to draw it first without components, and then we'll break things into components. So let's draw the free body diagram twice. So the original free body diagram is still going to be normal force acting out of the plane, weight pulling down. But now, how do I draw friction? How do I incorporate friction? What did we say before?
Going down the ramp.
Down the ramp. Very good. Down the ramp. And we know that because the car is going to have a desire to move out of the circle, which is up the ramp in this problem. The car wants to move up the ramp, so friction will keep it pulling down the ramp. What kind of friction is this actually here? What kind of friction is this? Okay, so I would say static. It's kind of both, actually. It's kind of weird. It's kind of both, because the car is technically, as it's moving, I know the wheels are rolling, but there can come times when the car was like sliding, right? But because it's preventing sliding left or right, the car doesn't want to slide up and down the ramp. So that's why it really is static. But in case the car did slide up and down a little bit, then it becomes kinetic. So it really is dependent upon the problem. We are going to assume from here that the car is not sliding up the ramp. It's stable. So we'll say it is static. But do you see what I mean here? So if your car started to like drift a little bit off the road because it was wet, then your car is sliding left or right and it becomes kinetic friction. So I just labeled it new for now, but it is absolutely going to be static friction, keeping it from sliding up the ramp. All right. Now, at this point, it may still be tempting to go back to our old school methods of inclined planes and put our y-axis here, our x-axis here, and then break this into components. Remember we've done that? The only reason I'm not going to do it, again, is because I need the forces acting toward the center. So neither of these forces are pulling toward the center. This is pulling down the ramp and slightly like this. This is pulling out of the ramp and slightly like this. So I need to break Fn and FFS into its components so we can see what's pulling toward the center. And if you're confused about what I'm saying, look back at the previous diagram and look at Fnx. That was pulling along this direction. So we need that again. We can't just use the x and y direction and tilt it, because then we'll never have a force acting this way, and we won't know what to put in for some of the forces in the circular motion part for this part that we're going to look at in a moment up here, right? So what we're going to do is we're going to now break this into components again. So it's really important that we recognize this. Fn, again, is the same. So there's no need to re-look at Fn. This is really Fn sine theta. This is Fn cosine theta. We already wrote this down a little while ago. This is Fg. So that's the same free body diagram we had right there a moment ago. I labeled sine theta and cosine theta instead of x and y. Well, FFS is also acting at an angle, but let's take a look at it. So let's go back to the other free body diagram. A little while ago we did this. Right? We did this on purpose so that we could validate that if this is theta here, this was also theta. Okay, remember we did this with a little movement around the diagram. So the question becomes, what is the angle theta that we're going to use for friction? Are we going to use theta and keep cosine and sine the way they are? Are we going to use 90 minus theta and keep cosine and sine the way they are? Are we going to use theta and switch cosine? You see what I'm saying? There's really a big question here. So let's draw another set of diagram here. Ready? So watch what I'm going to do. I'm going to draw in a horizontal right here. And I'm going to start labeling again. And if you need to label on your diagram, you should label on your diagram what these are. So this is theta, right? We don't know what theta is. But what is this then as a result? If this is theta, what is this right here? Everybody agree with that? Right? So let's write in your diagram, write that as 90 minus theta. If that's 90 minus theta, then what's this angle right here? Because this whole thing is 90, isn't it? And if this is 90 minus theta, that's got to be what's left over, which is theta. It's always going to happen this way. They're going to add up to 90. So let's label that as theta now. And that's the only angle that matters. This angle theta right here is the one that matters. And the reasoning is this. F, the force of friction, is a vector with an angle of theta between the vector and the horizontal. So do we have to switch cosine and sine? If it's between the vector and the horizontal, we don't. Remember earlier, it was that Fn was between the vector, the angle, sorry, for Fn, was between the vector Fn and the vertical. Remember, this was theta, which is the angle to the y-axis, which is why we switched. We made our vertical component cosine and our horizontal sine for that. But for friction, the angle that we're using is shown here that friction is acting this way and this way. So friction on my diagram is going to look like this. This is what's going to make it very confusing. And bear with me here. Friction is going to act down and to the left. So this red one is FFS cosine theta. This is FFS sine theta. So that's my free body diagram when friction is involved. So without friction, we go back to just saying, hey, what's in red is not here, right? Without friction, whatever's in red is just not there. But friction is shown in red in this problem, and I did not switch cosine and sine for x and y this time. Because again, the angle theta for friction is between the vector for friction and the horizontal. So I don't have to switch the sine and the cosine where I did earlier. I feel like I'm just making sure, I want to make sure that we understand the sine and cosine piece, because it's really important, that part. Again, I'm not switching sine and cosine because this angle is between the vector and the horizontal, whereas this was between the vector and the vertical. That's why we switched cosine and sine for Fn. At this point, it becomes another same problem. It's the same exact problem. Can you spend like a minute or two with the person next to you? I want you to go through the sum of the force in the y direction and the sum of the forces radially. Again, same setup, but it's going to look slightly different because we're going to have additional forces. And I want you to go through the process of practicing to solve now for theta for this scenario.
Down the ramp is a positive or negative in this case.
So it doesn't matter in this case, actually, because we're not looking at the sum of the forces along this direction at any point in time. What we're looking at is the sum of the forces radially, inward, and the vertical forces. So inward is positive for mv squared over r. That's all that matters. Down the ramp, turns out it doesn't matter. Good question.
Wait, Mr. I have you just clarify. Since we're not switching cosine, sine is the angle over here is the angle between the horizontal
And the vector itself. The horizontal and FF.
and then because over here we're switching against the vertical, right?
Correct, because Fn is between its own vector and the vertical. That's why we switch sine to cosine. But FF is between its own vector and the horizontal. Whenever it's between the horizontal, cosine stays with x and sine stays with y. It's when it's not, we switch it. And there was the same rationale for FG. When we break that into parts on the inclined plane, same exact idea.
Alright, thank you.
Yep. So I want you to just go through the process, right? Step yourself through it. I'll put it up as we go along, but I want you to do it yourself while you're waiting here.
Yeah, let's break it.
So I'm drawing in red what's changed, right? So in case you're wondering, this equation hasn't changed except what's in red. It's the only additional force acting vertically. So it's the same as what was up earlier. I'm just adding the red part in. And here we're going to have both forces now pulling toward the center. So we've still got this, but additionally we've got friction pulling toward the center to help the part in circular motion. Oh, I should put that in red. Sorry, I just said I'm going to do it in red. Oops. Remember, we're not looking at the x direction in this problem at all. The x direction is really the radial direction. It's radially inward that we're feeling this pull toward the center of friction and normal force. It just gets really messy, this problem. The solution is going to get messy, that's all. Yeah, it's definitely going to get messy. Replace F with its definition, right? Watch what's going to happen here. F is really mu Fn. So you're going to have Fn appear twice in the y direction now. Everybody see what I'm saying here? Because friction is mu times Fn, Fn appears twice now. And then we're going to have to take that Fn, plug it in here, and over here. You follow me? It's just going to get really messy. So it's up to you, algebraically, or just get a number for Fn over here. Because you can definitely get a number at this point, right? Fn is the only unknown variable. So to save yourself a little bit of headache of all the algebra, because the algebra is going to be really messy. We're going to solve for Fn by factoring it out, moving stuff around, plugging it in here and over here. I would at this point probably just solve for the value of Fn actually. Oh, I'm sorry, we don't have theta, so we can't. You're right. So we're going to have to do it algebraically, yeah? Sorry. Theta's the unknown here, right? Okay, so let's do it algebraically. Let's do it together if you're having trouble. So what I'm going to do is I'm going to move mg over, and I'm going to factor out Fn at the same time. Oops. Whoa. I'll show you what I'm going to do here. So again, I'm going to move mg over here first, because it doesn't have Fn in it. Then I'm going to factor Fn out of what's left on the left side, leaving me behind with cosine theta minus mu sine theta. This is why math is like so important that your skills are perfect, right? Because it's not easy the work we're doing here. Fn comes out here and here. Cosine is left over. Mu sine theta with the negative is left over. I took the mg and moved it over. I did all this in one step. And then really, if I knew my algebra well enough, I wouldn't even have shown that work. I would have gone right to the answer for Fn. God, I keep zooming out. Sorry, guys. I'm on the wrong button. I would then again say this. Fn equals mg over cosine theta minus mu sine theta. This is why the book doesn't do this example, because it gets 90. They don't actually go into this example. They go into, in problem 56, they have a problem with friction, but you're not solving for theta in that problem, because this is a very tough problem to solve for theta. All right, so now in the centripetal or the radial direction, we have to plug this in. But before that, we have to still do something in the radial direction. Let's make this look better. So this is still Fn sine theta, but then it's going to be plus mu Fn cosine theta. I got to replace that. Equals mv squared over r. It seems like it may be or may not be the case. Let's see. No, m will cancel still, it looks like, actually. Interesting. M will still cancel. Whereas a minute ago, I thought it wasn't going to cancel. Remember when I said to you guys, like, oh, when we involve friction, m will matter? It looks like it won't matter, actually, again, still. Because m is going to be here, and m is going to be here, right? In both of these spots for Fn, and then m is also here. So m actually will cancel, it turns out, which is not really realistic, to be honest. All right, so this becomes, and this is going to get really messy, so just bear with me. This becomes the following. And I'll do it in red. I'll show the substitution in red. Mg over cosine theta minus mu sine theta times sine theta plus mu times that same thing again times cosine theta equals mv squared over r. Again, I'm just replacing Fn in red in both spots. But that's why this is going to become a really tough problem, obviously. Mass cancels, so we can drop that off in all three terms. That's great. But unfortunately, solving this would take a little bit more work than we want to deal with right now. So what do you think I'm going to recommend for solving this? How am I going to recommend you solve this? Yeah, I would do it graphically. I would not solve this by hand at this point. Okay, personally I would. You probably could, and it probably would take a little while to get all your thetas collected and to cancel things out appropriately, but it's really going to get messy, especially because of the denominators here, right? The denominators are what are going to make this the toughest. If this was a simple cosine theta, then they cancel. If this was even just cosine theta, it's sine theta over cosine theta, it makes a tangent. So it makes it easy. But unfortunately, the sine theta doesn't really just cancel with these pieces at all. And we can't divide them in separately. So at this point, I would solve this graphically. I would not solve this algebraically. How would I solve this graphically? What do you think? How would I solve it graphically?
Put it all on one side and then make the x's the thetas and then graph it and then solve for n equals 0.
Yeah, you can move the v squared over r. Take this v squared over r and move it over. Set the whole function equal to 0, and then find the x-intercepts of the graph, or the roots of the function.
Between 0 and
Very good. Max, you followed up what I was going to ask. Very good. Max, your Max said between 0 and 90. Because what's going to happen with a sine wave? How many intersections are you actually going to have? How many times does a sine wave actually cross the x-axis in general? What is it? Infinitely many. Think about a sinusoidal wave. There's a good chance that you're going to get multiple answers for this because you have a sine cosine interacting here. So you might get a function that crosses the x-axis a couple times. There's a good chance that only one of them will be between 0 and 90 degrees. Okay, but it's beyond 90 degrees, then your incline is beyond 90, and what's going to happen to the car? It's just going to fall down, right? It may turn like that. Actually, it wouldn't if you drove fast enough. You can drive on the ceiling of a roof if you drive fast. The ceiling if you drive fast enough. Do you know that one? You should check out like those videos. That's negative lift. Remember last class we talked about negative lift with the spoiler? So if you're going really fast and you went through a tunnel and literally went like that in the tunnel, and there was enough negative lift pushing on the spoiler, it would push you into the ceiling, which would create enough friction to keep you on the ceiling. It would actually, the push upward would help with friction left to right, but the push upward would have to exceed the weight downward. It's like a car going through a tunnel, and then the car literally just goes up on inside like that. It's like a plane, the same way a plane does. A plane will barrel roll, right? When a plane barrel rolls, it's using its forces to balance it to keep it upside down. So technically speaking, this angle, Max, could go above 90, but for a problem like this, it wouldn't because of the geometric constraints. You're designing a road. The road would never have a bank turn that is so much above 90 that the car would be traveling upside down on this side of the bank. It would always be on the top side of the bank. Okay? I don't know what this turns out to be. If somebody wants to figure it out, we can get it. But again, Chris, what did you say? What should it be? Number less than 12 degrees. Okay? Less than 12 degrees. Okay. All right. I want to talk about period of functions. I want to talk about that real quick because your text assumes a little bit of prior knowledge, which I think you already learned last year, but I want to make sure we're clear on it. Okay, so I want to make sure we're clear about what this means. So let me just open up a quick new slide to do this. We'll look at a slide that has something like, or we'll look at a problem. See, now I'm off. We'll look at a problem that has something that says like, here, let's see. Okay. An object, I'm making this one up. An object is swung. Is that a right word? Swung, right? That's good.
Yeah.
It just looks like a weird word. An object is swung in a horizontal or in the horizontal plane. An object is swung in the horizontal plane so that it maintains circular motion. The period of revolution is 0.4 seconds, and the cord attached to the object is 0.2 meters long. Determine, should should be a capital D. Determine the tension in the cord if the object's mass is 0.8 kilograms. Okay, determine the tension in the cord if the object's mass is 0.8 kilograms. So this is very similar to the lab that we discussed that you guys did last year, where you're spinning a rubber stopper around over and over, trying to figure out what the mass of that rubber stopper is based on the hanging mass. That was a really interesting problem. This is a little bit more simplified, but involving the term period. So where does the period play a role in this problem? Where does the period play a role in this problem?
Speed.
It'll help you to figure out the speed. Very good. Very good, Chris. So we are looking to know, in a problem with circular motion, we definitely have sum of the forces radially equal mv squared over r. R is given, but v is not given in this problem. V is not given. So we know the time period is 0.4 seconds. That's great. How can we find out v from that? The time period is 0.4 seconds. How can we determine v from that value? Kara?
Well, V equals delta of somebody less T, so we can just use that.
And what's delta x, though? What do you mean?
So, let's watch the object is, oh, we would have to find the circumference.
Very good. Well done. So in this problem, if you think about it, the object is moving in a circular direction. So there's the object. So what is the distance traveled? It is equal to the circumference. So if I want the average speed, I want the distance traveled, and I'm writing speed for a reason, obviously, right? Because velocity changes. The distance traveled over the time. So really in this problem, it's the circumference divided by the period, which is really 2 pi r over t. So when we want to figure out the speed in a problem, sometimes we may not be given that value, or if we need to use speed, we may not be given it. So if you're given the period of revolutions, you should recognize that the circumference divided by the period will always give you the speed. The circumference, 2 pi r, divided by the period will always give you the speed. So now if we look at this object, and it's hard to draw this, but I'm going to try and draw it as best I can. Okay, there's the motion right there. I'm trying to draw the horizontal plane, okay? Like a lasso, like a cowboy with a lasso. Here's the object right here. This is your hand at the center, and the dotted line is the rope that it's attached to. And the rope just keeps pulling you toward the center as you spin this around over and over and over again. So we know that we're going to have, if we look at this object here, we're going to have tension pulling toward the center. And gravity pulling down. That's it. That's the only free body diagram forces acting on this object. Tension toward the center and gravity pulling down. Gravity pulling down. So first, let's discuss this problem. Can this happen this way? Can gravity pull down with no counter force upward? What would that mean? If gravity pulled down, if there was no force pulling upward, it would mean it must be accelerating downward, right? And that force that's unbalanced causes acceleration. This one can be unbalanced because there is acceleration. There is centripetal acceleration. We know that. When an object spins in a circle, there's centripetal acceleration. So this unbalanced force acting radially inward is what causes v squared over r, the centripetal acceleration. But can gravity pull down and nothing act up on it? It's not possible. Because if there's an unbalanced force pulling down, the object must be doing what? It must be accelerating downward. So does anybody remember last year? We made this in simplification. We made it really easy in the lab. And I set it up like this and I said, don't worry about gravity. It was regular physics, honors physics last year. It didn't matter, right? Don't worry about it. But we're going to worry about it now. So how could gravity be accounted for in this problem? How could the force of gravity be accounted for? Does anybody remember that lab specifically? I know it's not an easy thing to remember. Think about when you were spinning that rubber stopper, right? when you're spinning that rubber stopper, it went around in the horizontal plane. It definitely did. But was the tension acted directly inward? Remember what it looked like, the diagram? Chris?
Up.
Yeah. The tension is really like this. Imagine this being the rubber stopper. We'll do it just to make sure you will see it actually. It's more obvious if you see it happen. So imagine again that the tension, or the object at the end is the rubber stopper. Okay? So if I spin it fast enough, like really fast, because I'm spinning it so fast it'll look like it is perfectly horizontal. But even while I'm spinning it, so you guys can see a little better, what you'll notice is that the rubber stopper is slightly lower than where my hand is. And if I spin it slower, it becomes more obvious. Do you see the angle? Does everybody see the angle? So it's acting downward like that, so the tension is pulling upward at an angle. If I pause it, it's really like this. This is the path it's taking. It's not actually like this, it's like that. The tension is pulling up at an angle, actually. So if you spin it, though, really, really fast, you can hear it, right? You should be careful so it came off and hit one in the face. But if you spin it really fast, it'll practically look like it is at a perfect horizontal. But it's really never going to be that way. It will almost never be that way. It's just that the faster you spin it, what's going to happen is that this t value goes down, making mv squared go up even higher. So the faster you spin it, what we're going to notice is we're going to get more tension in the cord. More tension in the cord means it doesn't need as much of an angle. I'm just going through the whole problem already kind of in my head for you guys so you can see where we're headed. But again, the faster you spin it, the lower the angle will be. So this kind of a problem actually doesn't look like this. Instead, it looks something like the other part. It looks instead like it's got a bit of an angle upward in that direction. So really, a problem like this would have to be having an angle in it. So let's say for now, based on what you guys just noticed me doing, let's say that angle is about 5 degrees. I know it wasn't given in the problem, but this is really what tension would be. Tension would be acting at an angle of 5 degrees in this problem. So that's my arrangement really. So now, we look at this problem and we recognize ft sine theta. ft sine theta. ft sine theta. What does that balance? What does ft sine theta balance in this problem? FG. Remember, ft is here. The angles with respect to the horizontal, so keep sine and cosine the way they are. ft sine theta is this guy. It's balancing FG. So what is then providing the centripetal force acting toward the center? Not Ft, but what? What is this value going to be? If this one going up balances this, what is this force acting inward? Ft cosine theta. Ft cosine theta. So this free body diagram drawn the way it is, which is actually what it should be, really could be redrawn like this. A very short vector, Ft sine theta, Fg acting down, those are balanced, so I'm going to draw them at the same length, approximately. And then Ft cosine theta I know is much greater than Ft sine theta, because the angle is 5 degrees. So Kara, this kind of goes back to your question. This goes back to your question of, well here, with vectors drawn longer, right? And you asked this question a couple weeks ago, do we have to actually draw the scale? The reason here is because I know an angle of 5 degrees means the cosine function is greater than the sine function because it's less than 45. So Ft cosine theta has got to be more than Ft sine theta, so I purposely drew this longer. I then also said to myself, well, vertically we're in a state of equilibrium, so Ft sine theta pulling up has to equal Fg pulling down. So I drew these two vectors to be pretty much the same length. Then this is my actual diagram I'm going to use in the end. And what does it allow me to do? It allows me to do the following. Sum of the forces radially equals mv squared over r. Acting toward the center is Ft cosine theta, and that equals m. We know what v is. V is 2 pi r over t, and that's squared all over r. And where am I putting the v, or where am I getting the v from? Right up here. Remember, this is going in for v right there. So my equation turns out that I don't need the y direction. The y direction doesn't even help me with anything. But you know what? The y direction actually would give me the tension if I wanted to solve it that way also. So take a look and recognize this. In the y direction, give me about 30 more seconds. We've got Ft sine theta acting up, and FG acting down, and that equals 0. So I could find the tension in this direction, or I could find the tension here. So for a problem like this, what do you think is going to happen? Is it going to be only one unknown? Probably not, because how many equations do I really have? So there's a good chance that what is going to be unknown? Tension and probably theta. Follow what I'm saying here. Okay, because I can get tension if I know theta very easily in the y, which I do. I can also get tension right here. So there's a good chance that tension and theta will both be unknown in a problem like this. Here's homework I assigned for 6-3. Make sure you work on it. There's also multiple choice for 6-3. And I'm going to see you guys again on Wednesday. Okay? We haven't had something in a while that you could probably expect to have on Wednesday. So just start thinking about that, right?